So I don't know if this is a good spot after dinner, after lunch, or better before lunch, I don't know. Anyway, so wake up, because we're going to go and start talking about the edge. So as an introduction, you can hear from my accent, I'm not from Oz. I'm actually a Scot, raised in England. I now live in America. So if I say the wrong words, just forgive me. I always flip between router and router, and so just bear with me on that. Okay. So EdgeConnex, I don't know how much you know about EdgeConnex. We've been around about doing data centers for just under 5 years. In fact, we lay claim to the fact and the terminology of the edge. 4 years ago, we gave our PR firm the task of making the edge the sexiest thing on the planet. Now everyone talks about the edge, so you're welcome. So what I'll do, I'll talk about some of the reasons why the edge is important. And at the end, I'll talk a bit about what we do. And I threw a video in, because everyone had videos, so I threw one in at the end, just to show some of the things that we've done. It's a blatant plug, but there we go. So talking about why the edge is important. So right now, we live in exponential times. A lot of people use that term, but if you're not familiar with it, if I were to take 30 linear steps, I'd be at the back of the room. If I took 30 exponential steps, I'd be on the other side of the sun. So just to give you an idea of where that's going. And we have so much access to data, so much access to compute, that it's changing everything. And the pace of change is dramatically changing. And if we go back just a little bit of time in history, around 6000 BCE, most archaeologists agreed that's when we really hit the agricultural revolution. That changed everything in the world. That's where we were starting to control how much food we were producing. We could have surplus, we had cities, people were able to do trades. It wasn't just a hunter-gatherer situation. So that was a major shift in the whole of the world. Now, it took quite a while for the next big revolution. That was about 8,000 years, and that's commonly talked about as the first industrial revolution. That was primarily in the UK, where they started using steam engines. They had the loom, they started doing mechanization, and there was a move into more mechanized cities. You know, they had the workhouses and all of that, the spinning jennies and everything. So 8,000 years from the first to the second, then very quickly, there we go, 120 years later, we hit production of electricity in a more structured form. We had the invention of the light bulb, and as a Brit living in America, I often talk about it wasn't actually Edison who invented it, it was someone in Britain. But anyway, we won't go into that here. But then we had mass production, we had the assembly lines, and electricity was being distributed very, very readily. 90 years later, only 90 years later, we hit the invention of the transistor. We were sending people to the moon. That was a whole shift again, and most of us, we remember that, at least when we were younger, we remember seeing it on the TV, the Apollo programs. So automation, transistors, computing, and then the internet. That was the third revolution. And a lot of things happened in this time. 20 years later, we had the web. It was the web was released, the internet became a viable commercial entity in 1992. Just a few years later, 12 years later, we'd actually deconstructed and looked at the human genome. We could actually measure what that was. We could use that in a form. Then just a few years later than that, 6 years later, we'd actually had commercial space travel. You know, there was the Virgin rocket. I mean, it's not truly commercial yet, but that was a huge shift. We have 3D printing, very, very rapid acceleration. Now we're about on the cusp of the fourth industrial revolution. You know, we have 3D printing, IoT, VR, MR, distributed ledgers. We've talked a lot about blockchain and all those things. AI, machine learning, all the things that have been discussed today. This is the cusp of the fourth industrial revolution. And this is going to change so much for everybody. We're breaking down the barriers of the trust entities. We're not now just looking at entities to guarantee that we've moved money from one place to another. You know, Visa, PayPal, all of the banks. We're using distributed ledgers to do that. Governments are losing. But there's a whole shift in how things are moving. This will be one of the most dramatic shifts in human evolution. Now, to make this work, there's a whole bunch of activity and technology and infrastructure that doesn't exist today, or at least it doesn't exist in the form that's really going to make this a viable entity. So let's just talk about some of those things. We just look back at the computing power and how that's grown. This chart shows basically how many transactions per $1,000 you can get. So you go way back to the analytical engine of Charles Babbage. It was less than 0.00001 transaction for $1,000. But as we come up to today, you can see, I'm looking at this. As you can see, there's a whole raft here where it's come way, way up. And this was a great chart until the GPUs came out. NVIDIA really broke my chart. It was really nice until then. That's just taken it to a whole new level. It's broken the whole Moore's law. Instead of using the way the silicon's been developed, and they're using FinFET, so you can have so much more transaction capability on a single piece of silicon. This piece on the side here shows those transactions per $1,000. And if we look at the complexity of the silicon, you remember the Pentium 2? Remember the Pentium 2 and the floating point problems? Perhaps I'm too old here, but anyway. The complexity of that piece of silicon was the equivalent to the synaptic network of an insect. And I'm not saying the insect was as smart as a Pentium 2, but just looking at the complexity of what we're producing. If we look to about a couple of years ago, when we had the Apple Mac Pro came out, that was about the same complexity as a small mammal. If this carries on at the same pace, when we get to about 2020, for $1,000, if the big box stores still exist, we're probably going to have to buy online through Amazon and other distribution firms. But you can go for $1,000 US dollars, and it'd be the equivalent of euros and Australian dollars. You can buy a machine off the shelf that has the same compute complexity as a human brain. Now just think about that for a second. I mean, we're used to carrying around our smartphones, and we understand how powerful those are. For $1,000, the complexity of a human brain. Not necessarily going to be as smart as a human brain, but it has the same level of complexity. Now, if we take this to its logical conclusion, just in a few years, 2045, for $1,000, you'll be able to buy a device that has the same complexity and compute capability as every brain on the planet. Now, whether that's going to bring about the singularity, whether it's going to be the AI, whether they're going to send robots back from the future to kill us all, who knows? But in terms of the power and capacity that we're producing, just to move content around, move data around, and distribute data and make rational decisions about data, the power is exploding. So let's just go back a little bit again. There we go. And look at some of the key drivers of this transformation. Look at the macro drivers of data. So way, way back in the 60s, we had the mainframes. And the big names there, IBM, Burroughs, Unisys. And we measured everything in kilobytes. That was somewhere, it was pre-internet time, so between 67 and 92, that sort of time there. Then a couple of things happened. Around 92, we started having the rise of the PC. We were starting measuring things in megabytes. A whole new raft of companies hit the scenes: Compaq, HP, Microsoft, Oracle, PeopleSoft. And a lot of that processing, those jobs that used to live in the mainframe, we would have to go to discrete groups within the companies to go and get that data, started being distributed out to the businesses and the units that needed it through a lot of these PC technologies. That was our first wave of transformation. And when we get to about the year 2000, we start looking at things in gigabytes. And then there's a whole new raft of technologies with the advent of the internet coming on and actually being viable. As I say, in 92, that's when the US allowed commercial activity on the internet. And it took a while for that to spin up. But as more and more products came out, like Amazon, which didn't exist before, eBay, Yahoo, NetSuite, all of these products came to market, all these companies, and started moving data around much more readily. When we get to about 2007, again, the big pivotal change, that's when the iPhone hit the markets. There were a couple of things happening there. The Nintendo Wii started looking at mass production, and the iPhone, a mass production of components. It brought the cost down of so many units. So prior to that, if you anywhere between the year 2000, if anyone had a Magellan GPS device, it was about $2,000. It was fairly accurate, within 30 meters of where you were. But that same technology that delivers that capability is now about 5 cents in a piece of silicon that's in every cell phone that we have. So at this point, we start talking about terabytes of data. And then, again, a whole new raft of products and services hit the market, and the cloud becomes the dominant way where most people start thinking about running their business, doing their business. and putting their technology. Now, we're getting to the zettabyte, zettabyte era, and here we create about 2.5 quintillion bytes of data a day. That's 18 zeros. I had to go and look that up. That's an awful lot of data every day. But in reality, we only look at about 0.05 of that. So all that data is going somewhere. It's in these big data lakes. It's in and everything we've talked about today. It's the major data centers that are being built, and it's out there. At some point, we're going to find a way of monetizing that and just making a lot more money out of that. But we're heading to the yottabyte era. Now, if we start looking at how the internet access has changed, if we just go back just a few years, we were looking at lit buildings. We were bringing pipes in, getting access to data, and we measured everything in amps at that point. That was sort of the EPOP era. Then about 2012, which is when we started moving data and content much, much closer to the consumer, because we found there was a major issue with latency and delivery of data. It was driven mostly in the States by content. It was, frankly, it was Netflix. They bought a new catalog of data and was just crushing the internet as everyone was trying to get and stream internet content. And you remember that spinning wheel of death where we were just waiting for it. So there was a need to push that content much, much closer. And that's where we started building these edge data centers. They were about 2 to 8 megawatts in size. Just a few years later, those same cloud entities decided that as they were building these major sites, and you see it here in Australia, where particularly around the major metropolitan areas, you've got the mega clouds being built. And in the States, it's where land is cheap, power is cheap. It's in Oregon, it's in the Dalles, it's in Quincy, in Washington. So these are places where most people don't live, but there's tremendous power reserves, or there's hydro dams, or whatever it is. They're building a lot in Scandinavia, where they're using very, very cheap water generation. Even in Iceland, because they have virtually free power. The problem with Iceland is it's so far off the internet main routes that it's being problematic for them. So anyway, the hyperscalers needed to move portions of their data, again, closer to the consumer. Because it's all well and good having your mailer messaging hosted thousands of miles away. It might be really cheap, but if it gets out of sync and you're driving down the road and you're going to see a customer and your mailer messaging system goes through different paths on the internet and your contacts disappear, that's a bad day out. So a lot of them wanted to put those nodes much, much closer to the metro areas. And these were 20 to 60 megawatt sites. Now with 5G, when that gets ratified, we're going back to the small sites again, and we're looking at how we can aggregate a lot of that data. Because with 5G, you're going to have a tremendous amount of antennas. And in places like this, where the building's already set up for Wi-Fi, distributed Wi-Fi around the place, there's some technologies, the CBRS, where you can start leveraging, sorry, been there too long, that same core infrastructure in the building and do a handoff. So buildings like these, facilities like this, will be able to monetize access to the 5G networks. Because the wavelengths of 5G is as it was with WiMAX, it doesn't penetrate buildings very, very well. It's huge amounts of bandwidth, up to, it could be up to 50 gig bandwidth. It really depends on how it gets ratified and how it's deployed. But the throw isn't as far. It doesn't support as many active attachments, so you need many, many more antennas around the place. But anyway, so that's going to happen a lot. That's going to be a huge driver for smart cities. And then these smaller sites are going to be aggregated back many more times, and then that data will go back into the traditional architecture. So a lot of this has been talked about before. There's just a tsunami of data that's about to hit us. It's going to come from more and more users that are out there, more devices, more video viewing, and the Internet of Things, either commercial or domestic. Spending is predicted to be enormous. Compute and storage power is just going to go through the roof. And I won't labor the point here. You get the slides after the fact. But there's just so much more data. Every second, all of this is happening. In fact, this was a couple of months ago, so it's even more now. So, and here, in the last 2 years, we've processed more data than the last 2,000. In fact, there have been more photos taken in the last 6 months than the whole of history. And that's all, in fact, it's even less than that now. It's probably in the last 4 months. So, and you just imagine your kids, my kids, what we do, the photos you're taking of these slides here, a lot of them you probably won't look at again, ever. But, and all the Instagram, all the meals that everyone's taking pictures of and posting where they are, that's all being stored somewhere. So, as one of my favorite quotes from William Gibson, the future's already here, it's just not evenly distributed. So if we look at, as I said, the cell phone, it was the fastest accepted technology ever in human history. If you look at the charts, there's all sorts of charts which show, when electricity was in there, televisions, cars, but the cell phone is just enormous, and particularly the smartphone. So given that you could get access, a person in the middle of Africa with a smartphone in their pocket has more power in their hand than the President of the United States had, when Clinton was president, which wasn't that far ago. They have access to more data than they had in the 70s, more processing power than in the 70s. And with 5G, everyone with a device is now a broadcaster. So you think reality TV is bad right now? It's going to get a whole lot worse. So the problem we have is, and forgive that this is an American example, the internet was never designed for what we're using it for today. It was designed as a non-deterministic technology that could tolerate failures, lots of traffic from different routes and routes. It was designed for email, predominantly email, and it worked pretty well with some of the early web pages. But the idea was you would have a piece of data, you'd break it into data packets. Every point along the internet would look at where the traffic was, and it would just send it in whichever way, which didn't matter, because at the end it would be compiled and recombined into a logical piece of content. So speed wasn't really an issue. When we start looking at how we're using it now with video, with cloud access, if we start getting into pushing content out for mixed reality, this is just going to break. Also, it's by no means in enough places around, and again, forgive the American example here. It really focuses around the main peering points, which was a historical artifact from some of the early work that was done in developing the internet. And this, you could see exactly the same here across Europe as well, in London, well, the flap markets, as it's called, Frankfurt, Amsterdam, Paris, and London. That's where most of the peering occurred. That's where the traffic moved off from one network to another. And as a consequence, that's where the data centers started to grow, particularly around Ashburn and San Jose, Los Angeles, up in Seattle, in Chicago, and some of the New York sites there. We had a huge intake growth, as I said, of the mega clouds, and again, they moved again to where land was cheap, power was cheap. So that was the internet, and the content was living in those places, which again wasn't where it needed to be. Latency was a huge issue. Traffic has changed tremendously as well. The majority of traffic on the internet right now is content. It's not email, it's not web, it's video. Netflix is by far the lion's share of that. YouTube is growing dramatically. Amazon, as they grow, that's going to come up even more. And you have all these other ones here, like the BitTorrents and Hulus. Facebook, actually, in the new figures, Facebook will be much, much higher as they've started to push content out, particularly their streaming of live content. And on mobile as well. Mobile, Facebook is the dominant. So we know that we use our phones all the time. The majority of the traffic from the handset to the infrastructure is Facebook updates. It just is. That's how it is. And that infrastructure is struggling to keep up. How we consume video has changed as well. So we've gone from this 10-foot experience where we'd all sit around and watch TV as a family. Now we're watching it on a device. And sometimes concurrently, there's the big show going on, and then we're watching either a second screen with some of the data or watching something else entirely. It's just changed dramatically. TV is now a service, and a lot of the cable companies in America have seen that. So TV is just another service with an IP backbone. We're seeing that traditional live broadcast is actually going to be eclipsed. In fact, I think it's almost happened now, where over-the-top traffic is actually consumed far more, certainly in the States, where there's a whole plethora of not only the cable cutters, but the cable nevers. Millennials who are out of college, who are using some form of internet that they've got. They're probably using their parents' Netflix accreditation or whatever, but they don't bother buying the standard television. They just go straight to the over-the-top. Also, the broadcasters are changing. So just a few years ago, in August of 2015, Netflix hit 1 billion concurrent users in one day. Now they're over 2 billion a day. That's extraordinary, just extraordinary. And as that grows, it's just going to get more and more on the infrastructure. So, and there are a whole new bunch of broadcasters. So there's a couple of guys, and you've probably seen it, in Austin, Texas. They're the ones who throw the basketballs out of a helicopter or off a building. They have more traffic than the whole of ESPN's network in the States. So much so that Disney actually took ESPN.com offline, out of YouTube, took it offline so they could restructure and reform. So things are shifting at such a dramatic rate, so quickly. I don't know how much you know about Twitch. Looking at the age, who knows what Twitch is? Anyone knows what Twitch is? Excellent. When I do this in America, it's amazing how many people don't know about Twitch. So Twitch is one of the fastest growing broadcasters. They're the ones that enable gamers to rebroadcast what they're playing. And just if you look at the digital natives, the under 12s, if you look at any of them looking at an iPad or a phone, I guarantee they're probably watching someone playing Minecraft or World of Warcraft or something on Twitch. And Twitch is becoming one of the biggest broadcasters. They broadcast more content than HBO over the internet. And they're starting to do concerts now. They do a lot of the big gaming conventions. It's extraordinary how much traffic they generate on the internet. Now, given all this, the traffic is costing a fortune to move that around for the network providers. This was an example of one of our customers in Phoenix, Arizona. They were the largest cable company in that region, but they didn't have their own backbone, so they were leasing cable from a network provider to pull all the content back from Los Angeles. So we did some analysis. When Gangnam Style was hot on YouTube, it crushed them. It cost them a fortune because every single time someone requested that file, a unique request had to go back across this lease line back to One Wilshire in Los Angeles, across the street to El Segundo, to an EdgeConnex site to pull that content, to pull it all the way back. Someone else viewed it, it did exactly the same thing because it wasn't cached locally, it was pulling it across that network. So we put a data center there. It became the head end for that cable company. We talked to a lot of the content guys, the YouTube in particular. They devised the YouTube Island. It was the first time they put a smaller version of YouTube anywhere. They put that in our site. Immediately that region became a 4K streaming zone. So people stayed on it longer, the content was better, ad revenue was higher, and it's become a huge growth engine for that whole region. We've now brought peering into there, we've brought cloud on-ramps. Whenever we do this, it just changes the economics of those regions because it starts with content, we monetize it over a 15-year time frame, so it becomes very affordable. We bring in all the peering, we change the network traffic, and then we bring the cloud on-ramps and some of those smaller versions of cloud as they follow. So localization, so for those of you who are doing this and thinking about what the edge can bring, these are some things, I won't bother going through them because you have them, but it dramatically changes the economics of how you deploy content, or cloud, or IoT, or whatever it is you're going to be doing to bring that local to the market that you want to serve. 16 minutes, okay. Now, not only content, but IoT, we've talked a lot about that over the last, well, this morning and last night. That's going to be a huge drive. Now, the traffic that's generated by IoT is very different. It's smaller packets. A lot of it won't go back to the cloud. You don't need updates from your Nest or your August Lock or your smart lights to go all the way back to a cloud engine. It's just going to stay local or then just be broadcast to your phone. But there's going to be a lot more traffic going backwards and forwards. And industrial IoT won't really impact the internet very much because it will be localized in the factory that it's working on. It just sends some updates where it's necessary. But as this enables more smart devices, again, it's the economies of scale. As you get MEMS going out there, you get a lot more devices that can be a lot cheaper. People will find ways of monetizing that. And maybe we'll all be wearing cameras on our glasses in the next 2 years. We'll have augmented reality. And that's just literally around the corner. So as we start looking at how we're pushing more technology and more capability into the standard everyday things, is going to change how the internet traffic flows. And here you can see IDC predict that 45% of the engines that deliver that content will live at the very edge. Now, cloud is another huge driver. As has been said, there's a lot of, most of the workflows that can be virtualized have been virtualized. There's a lot that still sit out there on discrete servers in large data centers or actually in people's offices. Where they have been virtualized, then it becomes an economic decision whether you host it as a private cloud in your building, in a colo, or you put it in a public cloud. The major issue that we're seeing in the States in particular, and I think it'll happen here as well, as it's starting to happen in Europe, is the latency issue that I talked about before. So when you're doing a SharePoint update, if it's more than 30 milliseconds, it's not viable. It just doesn't work. So it's a huge issue to bring that content, those updates, those data paths, those email, whatever it is, just to get that cloud access local to the people who need to use it. Here's an example, because people think about the speed of light. The internet doesn't run at the speed of light. But if you were to look at the speed of light across from Ashburn to Silicon Valley, Ashburn's obviously one of the big hubs in the States, Silicon Valley the other one, it's about 25 milliseconds, the speed of light. When you start sending a ping, a single ping, through all the repeaters and the regens that go on, it takes it to 100 milliseconds. But again, the internet doesn't work that way. The internet's a non-deterministic technology. Invariably, as this example here goes, just loading a page at ESPN.com takes 175 milliseconds just because of how that packet structure goes. So again, we think about things very differently. We just assume that the internet's there. We assume that it's fast, and it's not. So here are some of the, and I won't read these things, but here are some of the big guys who absolutely understand that latency is the critical element for adopting and monetizing cloud technology. And here you can see this was some external work that we did. Sodexis did this for us, and it's actually using Megaport. Just the whole data path, it's just so much faster. It's over 50 milliseconds to do a full update, whereas through the internet, the same data example was up to almost 300 milliseconds. So again, using fast on-ramps, using cloud access changes the way the internet is structured. Now here's some of the other applications. I love this chart. This shows where the internet, where the cloud breaks. So you can see industrial engineering, IoT gateways, VR, all of these things have to be as close as possible to the very edge. You can go a bit further out with gaming, over-the-top video, but then when you get out to the traditional big data centers with no fast on-ramps, I mean, it's fine for large file downloads if you have time to do it. It doesn't work if you're doing a site-to-site replication for disaster recovery. But there's a whole bunch of technologies there that show. So I'm going to rush it because I'm running out of time. These are some of the, again, some external work that we did to look at Azure and Amazon, looking at Direct Connect and ExpressRoute. The same data paths or the same workloads over the same distance. It shows public internet doing 200 miles for Amazon, 4 milliseconds using an on-ramp, using Direct Connect, as opposed to 24 milliseconds on the public internet. Azure was much the same, and you see the different regions there. Again, it's boring when someone reads the numbers, but dramatic changes there. So as you're starting to look at the cloud, and particularly as you start to deploy your data center technology, look at how you can use things like Direct Connect, ExpressRoute, Megaport, Packet Fabric. These on-ramp cloud accelerators will change the economics for you and your customers, and it just accelerates everything. So if you're trying to sell those as services, I encourage you to look at these technologies to make them much more effective for you. So the cloud is out there. It's moved across multiple instances, also at this hyper edge, and I'll talk a little bit about that. As I say, we have these tremendous pieces of technology that we carry around in our pockets. Do you remember the time when you had a critical email that you actually went back to your desk and actually worked on that, or when you just did it all on your phone? That transition, I would challenge you to think about when you did that. Because as of earlier this year, or actually the end of last year, in terms of whole internet traffic, it flipped. So the majority of traffic now on the internet is on cellular, it's on Wi-Fi, it's on mobile devices, iPads, Samsungs, iPhones, all of those things there. So not only, I'm not talking about desktop, rather notebooks here. I'm talking about physical mobile devices, things you carry around. Also, in terms of traffic flow, and again, forgive the American numbers here. For those of you who know where Kansas is, it's right in the middle of the country. Not a lot goes on in Kansas, but they will be consuming more data this year than Los Angeles did just a few years ago in mobile data. And it's going to be exactly the same here. So the infrastructure needs to dramatically change because most of that will be data, not voice. And those infrastructures that were designed for telephony don't work very well with this amount of data being passed across it. So 5G, that'll solve with these, won't it? Of course it will. Well, it really depends how it's deployed and what you're going to be using. So this is a nice little chart. It shows some of the things that we're going to be using over 5G. I need to do it either. So you've got the on-the-go, the nomadix, the fixed machine-to-machine. And then this is really the sweet spot in terms of speed and capacity, the amount of data that will be generated and how quickly. So those are the things that the 5G is really going to be good for. The rest can really be served with 4G or LTE Advanced. But really, the true case will be devices or applications that need less than a millisecond download and have an enormous amount of data they're trying to pass. Now, the misconception is that voice and data travels the same, is treated the same. In fact, it is treated the same. So when data hits the cell tower, it actually goes to a CO, a MITSO. Then that data goes all the way back to the central office. Then it peels off to the mega clouds. So voice and data is passing on the same infrastructure, same glass in the ground that was designed for voice. So that's an issue. That's why we're seeing this huge issue with latency. And 5G will work exactly the same. So the latency, it's about 20 to 40 milliseconds from device to antenna. The backbone is about 20 to 40 milliseconds to get back to the element that it's trying to service or data it's trying to pull. With 5G and small cell, we'll have somewhere between 1 to 4 milliseconds of latency, depends on how it's deployed, but it's still going to hit the same architecture and then go back to this 20 to 40 millisecond problem. So what we're doing and what you could be doing is putting the smaller containers that aggregate those new cell antennas, and then it splits off the data. The voice will go back to the infrastructure. It'll be VoLTE, voice over LTE, or voice over IP. The data request to pull that YouTube video or that Facebook update or that email or whatever it is, will then go to an edge data center and then back to the cloud as it is. So this is the infrastructure that needs to happen. Also, once you start putting these micro edge data centers out there, all the guys, the majority of the traffic that's being generated or consumed on these devices, the social media, the video, the over-the-top, they all would love to have their caching engines as close as possible with those antennas. So it's another opportunity there for monetizing that technology. So it's not just telco. You're going to have mini colos, maybe bare metal that's going to be out there that can elastically be delivering technology out everywhere, everywhere we go. So, why does all this matter? Well, if you remember, there's an enormous amount of data that's about to hit us. The internet was never designed for it. So, blatant plug, this is what we do. We have edge pops, did those smaller pieces. We have so edge pops are in buildings, and there's a lot of in-building work to be done. Micro edge data centers out where the content needs to be aggregated, or we need to push the smallest capacity of content or cloud or on-ramp or whatever it is as close as possible. We have metro edge data centers, we have regional cloud, and we have the core cloud. And this has become the structure for us. And we talk about the edge. Everyone has a view of the edge. My opinion of the edge is this thin layer of demarcation between the service and the consumption. Irrespective of what those two entities are, the service could be a cloud, it could be a content, it could be anything you like. And the consumption could be a person, it could be a device, it could be an autonomous vehicle. Doesn't really matter. But it's moving that point of intersection as close as possible to the point of consumption, and moving those services as close as possible. So that, for us, that's what the cloud is. Oh, sorry, that's what the edge is, and that's why we have a portfolio that we go and deliver against that. So I'll show you a quick video, because everyone has videos. There was some sound, I don't know if I mentioned that, but yeah, this is how quickly we built over the last 4 years. See some of these, it's 45 days to build, 90 days to build. It's one of my favorite quotes. An invasion of armies can be resisted, but not an idea whose time has come. The edge is here. There's a lot of resistance to it. Content's coming. Infrastructure needs to change. We need to help people understand that needs to change, and we can make a lot of money in the process of doing it. So that's my talk, and that's just on time. So thank you.
Brilliant. Thanks very much, Phill.